Hello, my name is Alexis, and today I will be presenting on how runtime verification triggers real-time autonomous fault recovery on the CySat-I. The CySat-I is Iowa State University's first CubeSat. The number of CubeSats launched each year has grown exponentially. Their popularity is primarily due to their low cost and fast development times. Since the first CubeSat was launched, the failure rate has decreased over the years, but the failure rate is still troubling at approximately 25%. This failure is often due to lack of exhaustive integration and system testing. Most CubeSats will never have exhaustive testing, as one of the main attractive attributes of a CubeSat is fast development time. Runtime verification provides a unique solution. It can add an independent check for triggering of fault recovery strategies in real time, and provides different coverage than traditional system testing to allow for finding elusive errors with less effort, which I will show with a firmware error we discovered later in this presentation. One of the main reasons for CubeSat failure is a result of the electrical power system failing. Approximately 1/3 of CubeSat failures are attributed to the EPS. Therefore, we focus solely on the EPS within our research. The runtime verification engine we used is called R2U2, which stands for the Reliable, Responsive, Unobtrusive Unit. We selected R2U2 due to its low overhead, fast response time, and has been previously deployed on other hard real-time systems. We specifically are using the C software version of R2U2 on the OBC, or onboard computer. The OBC is the brain of the satellite and tells everything what to do and when. During flight, the EPS is responsible for charging its batteries from the solar panels and powering and enabling the UHF radio, payload, boost board, ADCS or Attitude Determination and Control System, and the OBC. Before launch, we compile the specifications regarding the EPS into a binary file and load onto an SD card on board the OBC. Specs are loaded once upon boot up. FreeRTOS starts a 5-second periodic R2U2 task, so every 5 seconds, the OBC requests information from the EPS, processes them, and sends it to R2U2. R2U2 reasons about these signals based on the specifications given and outputs the false values into an array. The OBC evaluates this array, and a predefined mitigation strategy is triggered by sending the appropriate command back to the EPS. To design our specifications, we wrote them in Mission-time Linear Temporal Logic, or MLTL, which is the base language used by R2U2, and allows for specification relative to mission time. Our EPS is a commercial off-the-shelf component from EnduroSat. Therefore, we are limited in the signals that we can request from our electrical power system. All of the available signals are shown here on the table on the right. To create our specifications, we want to specify about all available signals using the following 4 categories: operating range, rate of change, control sequence, and physical model relationship. Now we will go over a small handful of specs that we have developed. The ISS, or International Space Station, requires all subsystems besides the EPS and OBC to be powered off for the first 30 minutes. This specification captures this requirement. Since the R2U2 task is launched every 5 seconds, the global leap from 0 to 360 covers the first 30 minutes of launch. That is, 5 seconds times 360 equals 30 minutes. 30 minutes after launch, there are power bus requirements for the UHF radio, boost board, and payload required for proper operation. The UHF radio requires the latch-up protected 3.3 volt bus, and Specification 2 captures this requirement from 30 minutes to the end of the mission as simplified by the capital M. Corresponding requirements for the boost board and payload form Specifications 3 and 4. When the EPS encounters an undervoltage event, it increments its undervoltage event counter. By comparing the current value to its previous value, we can observe whether an undervoltage event has occurred. We expect there to not be an undervoltage event while in flight. Therefore, this specification captures that requirement. In order to evaluate the correct implementation of our specifications, deployment of R2U2, and correctness of our fault recovery, we conduct mock launches here on Earth. An example of how our mock launch works is shown here on the right. To emulate the ISS deploying our CySat, we turn on the EPS and OBC. An R2U2 task then begins, and FreeRTOS initiates UHF, ADCS, and payload task, which each wait 30 minutes before starting simplified operation. During our mock launches, the EPS and OBC communicate via I2C in the CySat stack. But our electrical power system also has a UART communication bus accessible via USB that connects to a GUI provided by the manufacturer that allows for external fault injection because we can externally turn on and off power buses and subsystems. R2U2 is a stream-based runtime verification engine that reevaluates specifications at each time step, creating an implicit global operator. Therefore, we have to take our original specifications and reduce them as shown in this figure, basically just taking away that outside global operator. In order to apply a specification for a certain time interval, the OBC monitors the current time step of R2U2. If not within the applicable time interval for a specification, the OBC does not care what R2U2 is outputting and does not apply mitigation action, which is indicated by the shaded region. Within the first 30 minutes, we first inject a fault by enabling the latch-up protected 5-volt bus. You can see that R2U2 immediately evaluates to false. Our fault recovery then turns off this bus within the next time step, and R2U2 evaluates to true. We can see that if we inject any faults for turning on a power bus or a subsystem within that first 30 minutes, R2U2 evaluates to false. Within the next time step, our fault recovery has turned off that power bus or subsystem, and R2U2 has now evaluated to true. After the first 30 minutes, specifications 2, 3, and 4 hold. If we inject a fault and enable the boost board, but our 5-volt bus has not been enabled yet, R2U2 evaluates to false. Our fault recovery will then enable the 5-volt bus by the next time step, and R2U2 will evaluate to true. We can see that if we ever turn off a power bus while a subsystem is enabled, R2U2 will evaluate to false, but will turn on the applicable power bus by the next time step, and R2U2 will evaluate to true. Now, when we evaluated our specification involving the number of times under voltage, we saw that it occasionally returned a value of false. So we wanted to dig into a little deeper and see why this was happening. We could see that the EPS was actually jumping between values of 10 and 2,308 for this mock launch, and this was reproducible across several mock launches. Jumping between two values like this is definitely an erroneous behavior that resulted in us contacting the manufacturer. This firmware error we would have most likely never have found using traditional system testing, and this is a benefit of using runtime verification. Altogether, we created 22 specifications. Even though I went through a handful in this presentation, they are all available as a benchmark on StarExec, as well as available on our Artifact website. We're also able to demonstrate successful fault recovery and demonstrate a firmware error. Future work would include deploying R2U2 on all subsystems, as well as continued exploration of using runtime verification for Earth testing of CubeSats. And lastly, hopefully we can observe our strategy in flight when our CySat is currently scheduled to launch in October. Thank you.